Hi, everyone. Thank you so much for joining us today for the Using Python 3 and the UEFI Shell for Platform Security Analysis webinar as part of the UEFI 2022 Virtual Plugfest. We'll get started in just a second here. Hi, everyone. Thanks so much for joining us for Using Python 3 and the UEFI Shell for Platform Security Analysis webinar as part of the UEFI 2022 Virtual Plugfest. I want to take a moment here to introduce you all to our presenters today. So we have Intel security researchers here, Aaron Frenzel, Nathaniel Mitchell, Sarah Batlery, and Dan Scott. I did also just want to do a shout out as well. We will be doing a live WebEx Q&A after this webinar wraps up. This is a chance to speak with the presenters directly and ask them any questions that you have that may not have gotten addressed during the live webinar or during the Bright Talk Q&A. And with that, I'll go ahead and pass it off to the presenters.
All right. Excuse me. My name is Aaron Frenzel, and we're the Chipsec team. We own the framework, releases, general support, and sustaining of the framework and tool. Our primary focus here is security research. Our talk today, as the title suggests, covers the Python 3 in the UEFI Shell for platform security analysis. We've broken it up into two parts here. First is a high-level overview of our prior shell, some of its pros and cons, a new opportunity with Python 3, issues moving from Python 2 to 3, our implementation of the UEFI Shell Python, and how to build it for your own use. Second is an overview and demo of how Chipsec uses this Python implementation within the shell, an overview and some examples. Nathaniel and Dan will be picking that up. All right. Hopefully you've heard of Chipsec before. We have a poll. How many have you heard of Chipsec? If you can, please participate. Please answer if you can. Thank you. If not, Chipsec is a security-focused Python-based framework and toolset. It includes test modules and pen testing type tools such as fuzzers, negative tests, platform utilities, and detection for known mitigations and security recommendations. Originally developed within Intel by Yuri Buligin, it was announced released by the Intel ATR Advanced Threat Research Team at CANSEC West in March of 2014 as an open source project available on GitHub. If you're not familiar with it, I suggest taking a look. Supports Windows, Linux, DAO, and of course, UEFI Shell, which is why we are giving this talk today. Hopefully this overview will be helpful introduction to the shell, use of Python, and how we utilize it with Chipsec. And here's some background. So our first Python for the shell used the Python 2.7 implementation from EDK to UDK 2010 sources initially. I believe we rebuilt it later using a subsequent version of the UDK. If I recall right, it was more of an experimental release of the Python EDK2 implementation, but did work very well. The UEFI Python 2 implementation repo has moved around a bit. I believe it was on Subversion for a while, but now archived in GitHub. Not sure if you'll find it elsewhere or what condition it'll be in. But for prosperity, for historical reasons, link to it, the README link as a reference. The latest should be there if you're curious. Our initial UEFI Python 2 shell release was released in March of 2014. It took a little while to stabilize around late 2015. Later, we added 64-bit memory addressing support in 2017. It was pretty good, really no issues, and it, it worked. So, however, it did have some court support complexities at the Chipsec level. We were supporting both Python 2 and Python 3 versioning. Not ideal. Right? As you know, Python 2 support was end of life January 1st, 2020. At this point, we really weren't seeing any functional or security updates to Python 2 anyway, way past time to move on. We had been looking at replacing Python 2 for a while, and this was really the last straw, of course. It needed to be replaced. And by the way, if you are using Python 2 with Chipsec, we recommend moving to the Python 3 port. Now, released in September 2021, NJ Prakash and Michael Kinney released an EDK2 channel core port of Python 3. You can find it within the EDK2 libc repo under the app package applications folder. All of the Python 2 content has been removed at this point, but is still is being archived. We were able to provide some initial evaluation of it and give some feedback. Major kudos to them for their efforts in getting this out. A huge thank you to them. We would likely we would likely still be on Python 2.7. Again, not ideal at this point. But we did leverage it and added our own content for our purposes. Python by itself really didn't offer, of course, the capabilities that we need. Which the next steps outlined later, we are what we brought in, things we came across, and how to add your own content as well, and how we build it. Now, since we already had the Python 2 implementation, we simply leveraged that for Python 3 here. Of course, since Python 3 fundamentally has some changes from 2, we had to make some changes from our previous code. Python 2 uses stir for strings and data. Bytes is a subset of stir and an alias for bytes, and does not automatically involve Unicode. So ints and long ints are separated. There's also some class differences and other syntax changes. Let's just say it's different enough to cause us some problems as a straight port. With Python 3, we had to make sure that our API stir supported Unicode and take binary data as bytes, and that we removed long int references. We also had a few instances of the deprecated U format specifier and meth old args calling conventions. Standard porting practice here for Python, really, but something we needed to consider, especially when we're relying on handling and processing data. Next are changes. So here's a summary of our routines, capabilities, and content we added to our version of Python UEFI Shell. It's not I'm not listing the code here, probably too deep of a dive, but it can be reviewed on the Chipsec GitHub within the UEFI folder. Within the EDK2 module C file. We did add our routines here for MSRs, SMI, PCI access, port, and some other additional APIs for the processor. We need these capabilities to run our tests. They expand on basically the normal Python capabilities and shouldn't alter any of the other libraries. So in the next few steps, I'm going to walk you through the process of building it. So to build a Python interpreter, you will need EDK2 and EDK2 libc source. I won't go too much into detail here. This is hopefully more of a review in this case. However, for additional details and more concise coverage, you can access the documentation linked off of the GitHub repos here. I've included a link to the README file that may be of use as well. Any up-to-date information or changes should be covered there. Also, I'm not covering any of the EDK2 build or tool prep steps. The build steps linked here should address that. So first step, clone the EDK2 repo and change to the EDK2 folder. You will need to update the submodules via this git command. There's a bit more context that needs or content that needs to get pulled in. Of that, it's done. Clone the EDK2 libc repo using git clone. So here are the basically summary of the changes that we brought in. Again, the files are contained on the Chipset GitHub repo within the Chipsec tools EDK2 folder. The two files here are really the only things you need to add to Chipsec to add the Chipsec content. The EDK2 module C contains all of the updated content. The CPU ASM contains all of the assembler code used by the new calls. And this part is essentially optional if you are only building the default UEFI Shell Python interpreter. You won't need these files and can skip if so. After cloning the EDK2 and EDK2 libc source, the Python source will need to be prepped. Within the Python 368 folder, run the source prep .py or source prep Python file. This copies the header files from within PyMod 368 subtree into their corresponding dictionaries and within the distribution. If you skip this step, Python will not build. I've inadvertently tested this in the past and can confirm. So you will experience, you'll get build issues. With the following steps, if you're not building, again, if you're not building the Chipsec added capabilities, you can safely skip them. For the modified code, though, you will need to override a file. There's an extra added file, and to modify a file. So with the first, you want to overwrite the EDK2 module C with ours. Second, drop in the CPU ASM into the modules folder. And last, modify the Python 368 INF file and add this line so that the CPU ASM gets built. You're going to need that. And time to build. So note, Visual Studio 2017 is known to work. I use it to build our implementation, the one currently on the Chipset GitHub right now. I've only tried Visual Studio and can't comment on any of the other tool chains. I believe that Visual Studio 2022 support has recently been added, so that's great. If you're using a different tool chain like GCC, make sure you update your environment per the EDK2 guidance, of course. All right. Now we can run the build command. This is for the x64 build. I haven't built x86 architecture. So I don't know if it works, unfortunately. But after the but so with this, after the build completes, it's fairly quick. If you want to create the Python package, this step again creates a folder containing all of the needed libraries and files required for the shell. It pulls in everything into one place, copies it, and whatever, self-contained. So there are two scripts for this: a .bat for Windows, and a bash script for Linux. Create Python 368 package bat and create Python 368 package.sh. You will need to specify the toolchain, build target, architecture, and destination folder where everything will go. Run that, and you're done. You've built the shell and encapsulated the Python 368 build. So almost, but December 2021, we committed our first UEFI Shell implementation to GitHub. Initially, we really didn't see any issues. However, for some reason, a handful of platforms exhibited this behavior when exiting the Python interpreter. The system would fault. Fortunately, I was able to track down the issue to the UUID library. To duplicate the issues, simply load the Python interpreter, import the UID library, and simply exit the interpreter. The system would fault. Turns out the routines used by the UID library for generating random UIDs was based upon environmental specific calls, mainly reading the Unix timestamp and MAC address of the system. It would check if Windows was the environment, and if not found, default to the Linux code. Obviously, this isn't Linux, and thus the system basically had a very bad day, and we get this error. UUID was soon updated, and the fix was in place that closer aligned with the UEFI environment. Again, a huge thank you to the submitters for the fix on this. We were able to get our implementation updated shortly afterwards and posted in May of 2022. So far, no other issues. So to run the UEFI shell, the process is pretty straightforward. You need a copy over the content created by the create Python 368 package script. From the previous step, extract the zip file or however you encapsulate it, or copy the zip file from our GitHub repo. The URL here links to it if you want that. But our GitHub release is in the UEFI folder of this repo. So on the right, the folder structure should look like this. Everything should be in the UEFI folder off of the root of your FAT32 formatted USB fob or drive. Python UEFI lives within the tools subfolder and the associated libraries within the standard lib folder. Yeah, you'll need everything here. That's pretty much it. Boot your system to the shell, and now you can run Python. So, now you can launch the Python interpreter, import the EDK2 library. As an example, we'll read an MSR, converting the value to hex, something more familiar, and we can verify that we're reading something from the platform. Word of warning, if you are trying to read an unsupported MSR, you will likely see issues. Your platform may fault, and well, it's expected behavior. But all of the Python commands and libraries should work as well, and it should look and behave like Python. And so debug support does work. So PDB loads and runs fine. It's actually quite helpful. So if you need that. So here's a summary of our added routines. These are all accessible now via Python. We can read, write memory, read, write IO, PCI, MSR, UEFI variables, as well as generate an SMI and call CPU ID. And then parse or modify within Python however we need. They may add. You can now add these to your Python scripts or tools or whatnot. Again, a word of warning: there's no guide rails on these. You could potentially poke something you weren't meaning to, or get some odd behavior. But maybe that's something you were hoping for. So yeah. Now Chipsec uses these calls within to work with within the shell. Hopefully, we can add more functionality over time and expand on this. Oh, this wraps up this section, and with that, hand it over to Nathaniel and Dan for the second part of the talk.
All right, I'm Nathaniel. So thank you all for joining. So as mentioned earlier, Python 2 was end of life back in 2020. And once the shell version of Python 3 was released in September, it took us of 2021. It took us a few months to get our support baked into the EDK library and update our Chipsec UEFI helper. This meant that we could officially drop support for Python 2 in all of our environments, which was really nice because then we could focus on just Python 3 and strip out anything that was either dependent on Python 2 or as shown in this picture, right? We had our own custom input function because we had to check the Python version and use the appropriate input to get data from the user. So now that we're on all of our environments, as of December of 2021, we can strip out all of these old functions and just clean up our framework and clean up our code, which has been really nice. Back before we found out that Python 3 was coming to the shell, we were considering just dropping shell support altogether for our framework. But shell is very important to Chipsec from a platform security standpoint, because lately the OS vendors, Windows specifically, but also to a lesser extent Linux distros, have been hardening the security and restricting what even kernel drivers are able to do to talk directly to hardware. So one of the easiest ways to get around that is to simply not go into the OS. So from the poll, I see that we have a wide range of people that have either run Chipsec a bunch or have never heard of it. So just looking at Chipsec, if you've run it before in previous iterations with Python 2, from the end user standpoint, not a lot has changed, because it is all still Python. So once you get your USB fob set up correctly and boot to the shell, it should look very similar to past experiences. So as I'm sure most of us are aware, you boot into the shell, you select to actually run Chipsec, you select where your code is stored, whichever file system. Generally it's FS0, but if you have more than one file system on your device, it might be a different number. Once you find it, you change your directory into the Chipsec folder, and then you call into the Chipsec entry points, either Chipsec main or Chipsec util. Dan will run through a quick demo on Chipsec main, but before he does, Chipsec main is mostly it's kind of a platform security unit test where it runs a bunch of modules or tests that will result in either a pass, fail, or a warning, etc. And all the modules that run automatically through Chipsec main are designed to be non-destructive. Chipsec util, on the other hand, lets the user interact with the hardware directly. So if you want to read or write physical memory, similar to the EDK2 functions, you can do all those things and more specifically with the Chipsec util. And it gives you a little easier time to just pass in arguments that you want to change. Yeah, so I'll pass it now to Dan for the demo.
Great, thank you. I will share my screen here real quick and give you a demo on setting up the USB fob for EFI Shell usage and running the Chipsec main tool. First off, we're going to start by navigating to the GitHub repository, chipsec/chipsec, and go into the latest release. In that page, you can locate the source code zip file, and you're going to want to download that. At this point, you'll extract, and it'll provide you the Chipsec root folder. And inside there, we can find the files required for the EFI shell setup. And you'll want to extract those to the USB fob that you intend to use. Once that's complete, we can navigate back to the top of the Chipsec root folder and copy that into the USB fob as well. And now you have your Chipsec tool and your EFI shell, and your USB fob is ready for use. In this instance, we'll be installing it into a Intel NUC and using that to boot directly to the EFI shell. And as Nathaniel was saying previously, you navigate to your file system in which your Chipsec root folder is contained and navigate into that root folder. And now the Chipsec main command can be called using Python 3.6.8. At this point, all the modules that are going to be tested are being gathered and compiled. It runs a little faster on USB 3. If you're using a USB 2 device, you might have a longer wait time. By default, the Chipsec main tool is going to output directly to the terminal window. But in use cases, it's often good to use the L flag and specify a file at which you want the log to be written for future reference or to submit to your development team. Here we can see the large output, and it can be also made more verbose. But we'll write this one up to a log file and go over some of the highlights of the document. Here we can see the top of the Chipsec main log. A couple highlights is the arguments on line 7. It'll show you which commands you used. The OS identification at line 10, as you can see, we're just using the UEFI shell and not an actual OS. Chipsec also provides platform identification and PCH identification. One of the modules being ran here, in this case, we can see that it's giving us a warning because the CPU supports mitigation, but the OS is not using it, as shown on line 154. This warning is because Chipsec is dependent on the testing environment. So while the CPU supports mitigation, we don't actually have an OS running right now. We're on the EFI shell, so the warning is expected behavior. And the log summary can be found at the bottom. It'll show a total of all the modules tried to run, the ones that passed, any that failed. As you can see in this case, most of them passed because the system was configured appropriately. We have some warnings and some non-applicables, but there are no failures or errors. If you have any more questions, please feel free to include them in the chat window and we'll answer them as we can. But with that, I'd pass it back to Aaron, or sorry, Nathaniel.
Thanks, Dan. Yeah, so wrapping it up, what's next? Well, please, we invite you to see for yourself. Feel free to run Python 3 in the shell. You're welcome to use our compiled version, which can be found on our GitHub, linked here at the first link. Or if you're adventurous, you can build it yourself with from EDK2 repo itself. And we also invite you to join the Chipsec community. So you can find our latest Chipsec release on GitHub. We also have a Discord server that hasn't been super active in the past, but the Intel Chipsec team is on there regularly monitoring it. So if you have any questions about Chipsec or any of anything that we do, feel free to jump on there. There's also a QR code in the top of the corner there that joins the Discord channel. Then we also have a quarterly community meeting that meets the first Friday of the last month of the quarter. And you can find information on our about our community meeting on our GitHub wiki. And then lastly, if you are an Intel customer with an NDA in place, working on platforms that haven't been released to consumers yet, feel free to reach out to us if you haven't already. And we have additional tests and platform support for those platforms that aren't public yet. And with that, I believe that is the end of our presentation. If there's any questions, feel free to type them in the box.
Great. So the first question here is, do you have plans to enable more recent versions of Python?
Go ahead, Aaron.
Yeah, sorry. Yeah, actually, there is some talk about that, possibly 3.10 or something. Definitely a lot newer. However, no dates or timelines or anything that I know of, or if it's currently in flight or not at this point. But yes, they're the hope is that we can definitely move to something newer. Although I have to say, 3.6.8 is definitely leaps and bounds better than the 2.7 we were using. So yeah.
Next question, is x84-64 the only supported architecture? How about ARM64 and RISC-V 64?
Good question. So far, our changes only cover x86, x64 versions of the platform. This is an open source project, and if someone can enable or has the capability of adding, say, ARM or any of these other platforms, give us a call, contact us. Our email is chipsec@intel.com, and maybe we can work together to get something committed, checked in, and out.
Is there any BIOS settings or configuration that's required before running Chipsec in the UEFI Shell?
You probably don't. You don't want legacy BIOS. You want to make sure that UEFI is enabled. That's probably the primary thing. And not all systems have a shell, from what I understand. So that could be a gate as well. And there may or may not be a switch associated with that. I don't know, Nathaniel, I'm thinking there might be a few other things.
In general, no. There might be some platform-specific configurations, but in general, the answer is no.
Can you run functions on AP cores?
Ooh. Don't know. Haven't tried. No, sorry.
in general, the UEFI shell runs in single-threaded mode, which I believe it targets one of non-AP cores. It might be possible, but we haven't investigated that specifically.
The next question, since we were able to run Python and Chipsec at a UEFI level, would it be possible to create a Chipset command that indicates the UEFI modules present at the BIOS that are not used? This is so we can check what can be removed from the BIOS without impact on the product.
It's an interesting question. I'm trying to parse this. Oh, wait.
Yeah, we'd have to investigate that. I don't know off the top of my head. That is an interesting use case, though. We'll take that back and investigate.
And then are you able to use additional Python modules, or are you limited to vanilla Python?
That's a good question. You should be able to add other versions of Python, or other modules. Although we haven't added any. That might be an interesting endeavor to see how well it works. I'm not aware of anything. I mean, if something relies on your environment, I mean, it is possible you could run into something that's, again, similar with the UID take or library. It's possible you could run into something that is looking for something like that. But as far as yeah, it should work.
Is the Chipsec tool a Windows-specific tool? Can we run it in all Windows versions?
Ooh, I think so Daniel, I think this was it. We have a list on our site of what versions, but up to Windows 11 is running right now.
Yeah, so it is not Windows specific. We run in Windows, Linux, and EFI Shell, obviously. Can we run it in all versions of Windows? The answer is yes, with the asterisk of Windows 11 implements some, as mentioned earlier, right? The OS vendors are hardening the ability for even kernel drivers to talk to the hardware. So there are some features in Windows 11 and I believe in Windows 10, but I believe they're enabled by default in 11, that restricts what we can do and how we can talk to the hardware. So that is, there's limitations on default installations of 11, but we are able to run on it.
Okay, great. And so with that, I think we can move now to the WebEx Q&A. So I'm displaying the announcement now so that you all have it for easy access. But we're moving to WebEx now, so you'll be able to chat with the presenters directly and ask them questions. And so thank you all so much for joining. The slides will be available on the UEFI Forum website, and a video recording of this will be made available on Bright Talk and then also the UEFI Forum YouTube channel. So thank you all so much.